So in the previous lecture, we looked at operations on search trees and we claimed that these were efficient if we could maintain balance. So let's see how we can keep search trees balanced. So recall that we are looking at these 7 operations. Okay, we want to be able to search for a value. We want to be able to insert and delete values. We also want to be able to compute the minimum and the maximum value in a tree and also find the predecessor and successor of a given value. And all of these we claimed would be order log n provided the tree is balanced. Okay, so that's because all of the operations as we implemented them will walk up or down a single path, and so the worst case would be the height of the tree, and in a balanced tree the height will always be logarithmic in the size of the tree. So today's this lecture, the goal is to explain how to maintain the balance as the tree grows and shrinks. So trees, there are many different notions of balance in a tree. So essentially a balance, you should think of it as like a physical balance, right? So if you go to an old style vegetable seller, then they will have this kind of a balance. And then you want, at any point, if you hold up a tree by its root, the two sides should be balanced. They should be equal, right? So the most direct notion of balance is that the two are exactly equal. That is, the number of nodes at the left is equal to the number of nodes on the right for every node. But then it's easy to see that you're going to get complete binary trees. For example, you could have a tree which has this structure. Or if you extended one more level, then for every node on the left, you must extend on the right. But then these must also be balanced. So you must definitely complete this. So you can have a tree up to 3 levels, which is completely filled, or up to 4 levels, and so on. Right? So if you want this exact size balance, then it's very restricted. So you might have a little bit more flexibility. You might say that, okay, we don't want it to be exactly equal. Maybe we want it to be at most one off. Then you could have structures, for instance, like this, where you have only a left, or you have at this point a left and a right, but you have only a right. Okay? These type of structures now, which are not complete binary trees, become balanced in this notion. So this allows us more flexibility and we can get more trees this way, but it is difficult to maintain this property incrementally as we do inserts and deletes. So we will go for a different notion of balance. Notion of balance that we will use is not with respect to size, but with respect to height. Okay, so we will say that the height is the number of nodes from the root to a leaf. For example, if I have a tree which looks like this, then here the height is 1, 2, 3, 4, because on this path we have 4 nodes, right? So the height becomes 4. It's the length of the longest path measured in terms of nodes. The reason we measure in terms of nodes is then we can distinguish easily the empty tree from the tree with only a root. If you measure in terms of edges, the tree with only a root will have height 0 because there are no edges, and so would be the empty tree. Whereas if we measure in terms of nodes, okay, then the empty tree has height 0 and the tree with only the root has height 1. So we can distinguish these two. And now, in keeping with our earlier relaxation of the size condition, a height balanced tree will be one where the height of the left and the height of the right differ by at most 1. Now this is more relaxed than the previous thing. For example, now of course I could start with a height balanced tree like this, okay, and then I could now connect this to form a height balanced tree like this, right? And now this, which is a height 3 tree, I can connect with a height 2 tree, okay, and form a height balanced tree which looks like this. So the height of the left subtree is 3, the height of the right subtree is 2. In this, recursively, the height of the left subtree is 2, the height of the right subtree is 1, and so on. Right? So we could have things which look quite different. So size here, for instance, size is 4 and size is 2. Okay? But nevertheless, you can kind of compute that the size, even in this case, will be exponential in the height, or rather the height will be logarithmic in the size. So these trees are called AVL trees. They're named after the 2 people who independently invented them. One person called Edelson-Welsky and independently Landis. Okay, so an AVL tree is a height balanced tree which says that at every node the height of the left and the height of the right subtrees differ by at most 1. So let us refer to the difference between the heights as the slope. Okay, so we have intuitively in our picture. So if it's unbalanced, then the thing is tilted. So we could have a tilt this way or a tilt this way. So we call this the slope. So we let us say the slope is the height of the left minus height. So the height of the left is less than the height of the right, then you have positive slope. If the height of the left is bigger than the height of the right, then you have left is smaller than right, you have negative slope. Left is bigger than right, you have positive slope. So in a balanced tree, since the height difference absolute value must be 1, you can only have 3 possible slopes throughout the tree. Either there is no slope, they are exactly the same, or it is minus 1 or plus 1. Now if you can argue very easily that if the current values of the slopes are minus 1 plus 1, when you delete a node, you can reduce one of the heights by 1, so the difference can go from 1 to 2. Or when you increase, you can make the height difference again go from 1 to 2. So the new slope after a single insert or a single delete can be at most minus 1 or minus 2 or plus 2. So what we will try to do is that whenever we do an insert or a delete, we'll immediately try to rebalance the tree. So we will have a single disturbance from to minus 2 or plus 2. It will never become very badly unbalanced, and we will immediately restore the balance to within minus 1 to plus 1. Okay, so we will do this rebalancing. We will also do this rebalancing bottom up. So what happens when we do an insert, if you remember, is that we go down and we find a place to insert. Right? So at this point we add a new node. So therefore now at this point there could be some imbalance. So we'll fix it. Then we'll go back to up this path and we'll go there and we will fix the path here. But at this point we will assume that the tree below has been balanced. Right? So whenever we rebalance a slope which is outside the range, we will assume that the subtrees below that are already balanced. Okay, because this balancing, as we will see, is going to be done bottom up. Right, so here is a typical situation that we would reach after a single operation which removes the balance. Okay, so we might have a node which has slope plus 2 or minus 2. So let's look at plus 2. Minus 2 will turn out to be symmetric. So we have a node which we call x, which has slope plus 2, and what it means is it has a left tree and a right tree such that the height of the left tree is 2 more than the height of the right tree. Remember, the slope is height of left minus height of right, so h plus 2 minus h will be 2. Now recursively we are going to assume that all the slopes here and here are at most plus 1 or minus 1. Okay, so we are assuming that everything below this has been fixed and the only imbalance in this subtree at x is at x itself. So now since the left has height h plus 2, okay, it has height at least 2. H can be at smallest h can be 0. So it has height at least 2. So there is at least one node here. I mean 2 means that there are at least 2 nodes here. So there is at least one node in particular. So we will expand this. Okay, so we will expand this by exposing its root, and the root will have in general 2 subtrees. Right? So now this whole thing has height h plus 2. Okay. So we will now look at this new node that we have extracted. Right? So its slope is minus 1, 0 or plus 1. Okay, and we are going to do some bottom-up rebalancing. We are assuming everything below is okay. So we are going to do some case analysis based on what is the slope of y. So let's first look at the situation where the slope of y is either 0 or plus 1. So if it is 0 or plus 1, it means that, so remember this whole thing was h plus 2, of which one node is here. So its left child must be at least h plus 1. And because the slope is 0 or plus 1, the right child is either h plus 1 in case the slope is 0, or it is h in case the slope is plus 1. So now this is the current situation as we have it with an unbalanced node x. Everything below is balanced, but we have just come to a situation where we are trying to analyze what is the situation below. Right? So x has got a unbalance of plus 2, and below it we have y, which we are assuming is either 0 or plus 1. So now we do this rotation. So we take this tree and we kind of hang it up by y and we reattach things. Okay? So in this rotation, when we hang it up by y, x comes down. Okay? And now we look at the subtrees. So we have these 3 subtrees, right? We had TLL, TLR and TR. So TR is to the right of x and is also to the right of y. Okay, so it is the right of both. TLR is to the left of x, to the right of y. TLL is to the left of y, left of x. So if we go there, we find that TR is to the right of both. TLR is to the left of X, right of Y, and TLL is to the left of both. Right? So we hang up these trees. So now all the values you can verify will be correctly organized as a search tree should. But now if you look at the slopes, we have just inherited the slopes from what we knew, that the slope of TLL was H plus 1, TLR was H plus 1 or H, and TR is H. Okay. So this means that if I look at this overall height at this point, it is either H plus 1 or at most H plus 2. So this is H plus 2 or H plus 1. Okay. If it is H plus 2, then the height slope at Y is minus 1. If it is H plus 1, then both sides are H plus 1, slope at Y is 0. And if we look at X, okay, here we have H or H plus 1, and here we have H. So the difference is either 0 or plus 1. So X is now balanced, Y is balanced, and by assumption, inductively, all the gray subtrees are balanced. So by one right rotation, okay, we have rebalanced the tree. So the third situation is that it is not 0 or plus 1, but the slope at Y is minus 1. Okay. So we have already dealt with the case where 0 or plus 1 is the possibility. So if it is minus 1, this means that the right subtree must be strictly taller than the left subtree. So this whole thing, remember, again is H plus 2 by assumption, because the whole thing has plus 2. So this whole thing is H plus 2 and this thing is H. Now this H plus 2 has now been split as Y and the rest. Therefore H plus 1 must be coming from the right and H from the left, because the slope by assumption we are assuming slope is minus 1. So now we are going to expand out this node. Now it's H plus 1. So there is at least one node here. Even if H is 0, it has at least a root node. So we will expose that root node as we exposed Y earlier. Okay, so now we have kind of expanded this TLR as Z with two subtrees, TLRL. So this is supposed to indicate that I start at the original tree, go left, go right, and go left. So TLRL, go left, go right. So it's TLRR. So that's the notation for these subtrees. Right? So this whole thing was H plus 1. So therefore this H plus 1 came from either side. So either this is H or H minus 1, or this is H or H minus 1. Okay, at least one of them must be H. Because if both are H minus 1, then the whole thing cannot be H plus 1. Right? So at least one is H, and it is balanced. So I don't know which way it is, but at least one of these trees has H, the other one could have H or H minus 1. And it turns out it will not matter which one has it. So now I have a two-step procedure. What I will do is now I will do a similar rotation but to the left, involving these two nodes. Right? So I will hang up these subtrees here by Z. Right? So if I hang up these subtrees, then what happens is that these three trees below have to be reattached. Right? And we reattach them in the correct way. TLL is to the left of both Y and Z. TLRR is to the right of both Y and Z, and TLRL is to the left of Z and to the right of Y. And now if you go back and check all the heights, then you find that at Y, I either have height 0, okay, or I have height plus 1. Now if I look at Z, then the left hand side is now H plus 1, okay, and the right hand side is H or H minus 1. So if it's H plus 1 and this is H, then I get plus 1. If it is H plus 1 and this is H minus 1, I get plus 2. So in the process now, not only did I have X which was unbalanced, I have temporarily created a Z which potentially is unbalanced. So I cannot say for sure it's unbalanced, but it could be unbalanced because I don't know which is H and which is H minus 1. But this is only an intermediate step. So now what I did, so earlier what we did was we did on left rotation here. Right? So I'm going to follow this up by a right rotation at X. So if we rotate right at X, Z goes up, X goes down. And now again we hang off the 4 trees, and there's only one way to hang off. You can verify if you go back and check how they were hanging. So TRR must be bigger than Z and X, TLL must be smaller than Y and Z, and so on. And now we have a very happy situation, which is that if you look at the slope of Y, then it is either 0 or it could be plus 1 because this could be minus H minus 1. If I look at X, it could be minus 1 because this could be H minus 1. This is definitely H, or it could be 0. But this whole thing is definitely H plus 1 because I do have at least one subtree of size H. This whole thing is again H plus 1 because I have at least one subtree of size H, and therefore the slope at Z is 0. So all 3 nodes X, Y and Z have slopes in the correct range, and therefore again I have restored the balance. So to summarize this, what we have said is that if we have plus 2, then we look at the left child of x, call it y. Now, if the slope of y is 0 or 1, we rotate right at x. If the slope at y is minus 1, we first rotate this and then we rotate y. Either case we rotate at x, but first we rotate at y in case the slope is minus 1. Now it will turn out that if we have the other case, the other extreme where the slope at x is minus 2, then we'll have a symmetric picture. So we will be able to expose the right child, call it y. So then the basics operation is that if y has slope minus 1 or 0, it's symmetric, remember. Okay, then we will do a single left rotation at x. Otherwise, we will first do a right rotation at y in case the slope at y is plus 1. And then we will do a left rotation at x. Okay, so we will not look at the minus 2 case in detail, but it's easy to see that it is symmetric to the plus 2 case. Okay, so how do you do these rotations? Well, you can just draw these pictures and figure it out. So you just give names to everything. So we say that we want to rotate this x down and the y up. Now we have our original t pointing here, remember, right? So we cannot change the node that t is pointing to. So we remember the value at t, we remember the value here. So we give these names x and y to the contents. And then we have these pointers pointing to these three trees, TLL, TLR and TR. And then we reconnect them. So what we do is we first replace this value by y, right? Then what we do is we make this node come to the right and we reset its value to x. Okay, so we put an x here and we have moved it there. And then we hang off below the top node on the left, we put TLL. And below this new right node on the left, we put TLR and the right we put TR. So we just do this kind of reconnection. It's like unhooking and rehooking trees, and we just keep track of all the names so that everything gets unhooked and rehooked correctly. So it's a very simple. So notice that this is a kind of constant set of operations involving a few of these left and right pointers. So it will, regardless of the size of the tree, it's a very local operation. So we can treat this as one constant unit of operations. Okay, and a similar thing for the left. Okay, we give names and we just do this updating exactly as we had done before. So again, this is a constant set of operations which implements rotate left. So now that we have the two rotations, okay, then what does rebalancing say? Rebalancing says that if I have a node which has plus 2, then I will expose its left child, okay, and I will check its slope. If its slope is minus 1, then first I will do a right rotation there, sorry, a left rotation there. And then regardless, I will do a right rotation at the top. Okay, and the symmetric cases, if I have a slope which has minus 2 at the top, then it will have a right child. Okay, and then if this has plus 1, then I will first do a right rotation here, and then regardless, I will do a left rotation at the top. Okay, so rebalancing is these two steps, and rotation is a set of other steps. So basically, rebalancing at a given node is a constant number of operations at that node. So now what we do is every time we make a change in our tree which could affect the balance or the slope of a node, we do a rebalance, right? So in our earlier code for insert, when we did a recursive insert in the left of a tree, we rebalance it. Similarly, when we insert on the right of a tree, we rebalance it. So we just introduced this rebalance code and notice that this is a constant operation for this node, right? So we will do this all the way along the path. So this will be a log n times a constant number of operations. So this will not affect anything in terms of the asymptotic complexity of our operation. It will be a logarithmic number of constant time operations for each node. The same with the delete. Wherever we do a recursive delete, we rebalance. And then there was this case where we deleted the maximum value of the predecessor. So again, we do a rebalance. Right? So wherever we had our insert or delete affecting the structure of the tree, we just make sure that we rebalance the tree at that point. So there is one point we have to be a bit careful about in this thing. So we said that we have to do all these rebalancing. So if you go back to rebalancing, okay, so rebalancing requires us to compute the slope. Okay, and slope we said was defined to be the height of the left minus the height of the right. Now it is possible to compute the height on the fly. The height of a tree is recursively computed. If it is nil, it has height 0. Otherwise, you recursively compute the height of the left and the right, and then accounting for this node, you add 1 to that. So you take the maximum of the two subtrees and add 1. But this unfortunately involves examining every node in the tree. So this will be proportional to order of the size of the tree, right? So this will be an exponential operation in some sense, depending, I mean, so compared to the path. So we are trying to do a log n operation. This will be an order n operation. Okay, so this will be killing all our attempts to do something efficiently, because in order to compute the height, we actually have to see the entire tree, which is not what we want to do. But we can get around this by just keeping the current value of the height and updating it each time. Right? So we have an additional thing. So we have in our tree node, we currently had the value parent, left, and right. Right? So now we just add one more field called height. Right? So now whenever we do any rebalancing, then the height of this tree may change, the current node. So we just look inductively, we assume that below us the height got set correctly. So we look at the two heights which are locally there, add 1 to the maximum of 2. Now this is just looking up one value in our two neighbors below, the two children. Right? So this now becomes a constant time operation. It doesn't require us to traverse the entire tree. So as we are rebalancing, we readjust the heights. And every time we want to check the slope, we just have to check the value of the two trees below us and check the difference of their heights, because that will be given locally by this height field in the node. Okay, so we have to be careful not to compute height recursively, but to store the height as part of the tree and also update that with every update. So to summarize, you can use rotations to maintain height balanced binary search trees. And in a height balanced binary search tree, we have claimed that the height is going to be logarithmic in the size. And since all our operations are proportional to the height because they all go along one path, all these operations, namely find, insert, delete, minimum, maximum, predecessor, and successor, can all be done in logarithmic time.